Welcome everyone, we're ready to start. Today we'll talk of NAT, Network Address Translation. This is our first specific example of a violation of the TCP-IP architecture. Here is an example of a network at home where I have 192.168 addresses, which we have seen are private addresses, so they're perfectly valid for communicating between one piece of equipment and another, sending a file to the printer, for example. But here, we would like to communicate with these addresses to the global internet. We're violating the architecture because we are using a private network, and also because the middle box here is not a router, but a network address translation box. A secondary goal of this invention is not only to use the private addresses, but also to be visible on the internet with only one IP address. Typically for IPv4, IP addresses are not so many, even though we have 32 bits, that gives 4 billions, which is compared to the size of mankind, and the number of devices we have is small, so we don't have enough addresses to give an address to everyone. The solution to that is, in principle, to move to IPv6, but people have found a hack. Instead of going to the clean solution, which is to move to IPv6, instead of that, well, you stay with the old IPv4 addresses, and you find a way to use that single address that Swisscom or others give to you at home and appear to the rest of the world as only one address here. So the goal is to use private addresses and to use the same IP address. So when you use NATs and you have several devices at home, to the correspondents on the rest of the world, everything is as if you had one single device, one single IP address, and multiple processes coming from that unique address here. It's used, as I mentioned, in residential networks. It is also vastly used in companies. In fact, most company intranets are using 10-something addresses, and they are using techniques like NATs to communicate with the rest of the world. Here. What does a NAT do? So the trick is to modify the IP address. For example, here I'm showing the internet with this address, 130 something. That's a public address, an address, imagine, given by Swisscom to you. So when a packet is sent from B to the rest of the internet, what the NAT will do is change the IP source address and replace it by this address, the address of the public internet here, which is, in principle, what a router never does. So a NAT is definitely not a router. It's a special box that changes the, obfuscate, if you want, the IP source address. Of course, while doing that, we have a problem of collision between A and B. If A and B are contacted some hosts, then the hosts don't know which are A and which are B. And when the packets come back in the reverse direction, the hosts usually respond by replying to the source address. So we will not know whether the source address, which is now the destination of the reply, is A or B. So we have a problem. We have a fundamental problem. The IP architecture says, well, normally the final correspondent host should use the IP address of A and B. But here we don't do that. The trick, which is very smart or very dirty, as you want, consists in playing with the port numbers. Port numbers are fields that we have seen are used by protocols like TCP and UDP. When B sends a request to a web server, for example, that request is sent to an IP address and to a port number that identifies the process in the web server that is performing the web service. By default, it's port 80 for web server. But there are also, that's the destination port, but there are also source ports. So when B is sending some traffic using TCP, it will have to use a source port, which is the port number that will be used in the reply. So when the server replies to B, it will send a packet to, if there is no NAT, to the address of B and to the source port, what was the source port in the message received by the remote server, and is now the destination port. This is used to provide the answer to the correct process inside B, because a machine typically has multiple processes that are connected to the internet. So this is to identify to whom inside the machine you should send the data. That's the normal use of ports. Here, this use of ports is cheated upon by saying when A and B send data, for example, to the same web server, they will each have their own port number that may be the same or are not the same. It depends on the randomness of when the ports are allocated. The NAT will also change those port numbers. So the NAT not only modifies the IP address, but it goes into the TCP header and modifies the port number, if it's TCP. If the packet is not TCP, most of the time it is UDP. So the NAT must know whether it's TCP or UDP and must know where the port number is and change it. So in that case, for example, we have two machines, A and B, that are sending, in that case, a UDP message, for example, a DNS request to some server. And assume, for example, they both used by accident the same source port number, 1029. What the NAT will do when it receives a packet that has this source IP address and this source UDP port number, it will modify them. It will modify by taking as IP address the IP address of the internet connection. Here there is no choice. And then it will find any available port number, for example, this one, 3441. And for the second packet, there would be a collision if we would use the same port number. So it will have to find a different port number than the one that was originally put by A. So those two packets will be sent over the internet. And for the correspondent host, it is as if you had one physical machine at this address with two processes that are sending requests. So that is the principle. That is now illustrated when a packet comes back from the server. For example, a server responding to this packet, it will send it to this address and this destination port number. The NAT will have to keep, of course, a table with this information and will, in the reverse direction, transform this address and this port number into this combination. And, of course, similar things to A with a different combination. How is this mapping done? Well, it's typically done on the fly, although you can, if you can manually go into your NAT at home. If you have ADSL, your ADSL box is performing the NAT function. So if you know how to log into it, you can go into the NAT table and perform this mapping manually. But in principle, we don't need it most of the time because normally the normal use of residential network is the servers are not in your residential network. The server is somewhere out on the internet with a publicly available IP address. So normally, when A contacts someone, it is not the someone that contacts A. If that would be the case, we would have a problem because the table entry cannot be built on the fly. For example, here, for the first time where a packet is sent from 1011, which is B machine, to the TCP port 1765, when that happens for the first time, so B is contacting a server that is responding to this IP address, and this port number, 80, sorry, this is the source port number. So B is contacting a web server. This port number 1765 is the port number that was allocated by the operating system or by configuration of the socket. We will see that in lab 3. It's allocated for the communication, and this is sent here. Now the NAT will screen all packets. And whenever it sees a new combination, which is the case here, the red one is a new combination, it will do a bit of work. It will, so for every packet that goes, it goes through the table and see whether this combination of source, IP address, protocol type, and destination port number is already in the table. If it is in the table, you use the table to match. If it is not in the table, you create a new entry, which means finding a new available TCP port number in that case, and keeping it in the table. So when this entry is created, we will see that the packet will appear to be coming from port 2343 and from this IP address as we saw before. So that's the principle. As you see, it's a hack. It's doing things that the architectures say you should not do. An intermediate box should not fiddle with the TCP port numbers. The TCP port numbers are end-to-end in principle. They're used only by the source of the communication and the final destination. But here, you do it. Sometimes it doesn't work. For some application, it doesn't work. The problem is if typically a server is behind a NAT. So if you have, for example, a server to control your house, your heating, your lights, your everything, and you want to contact it from the public internet, well, you need here, here there's amusing flipping of the characters, you need to map the IP destination address, which is not the address of the server, but the address of your NAT, of your ADSL access. You need to map that and a destination port to whatever the NAT would do. So the basic operation of a NAT is you create those entries on the fly, but on the fly works only when the communication is initiated from the private part of the network. If it's initiated from the public part of the network, for example, you are at a friend's house, you want to switch on your light by talking to your server, and then you want to communicate with this server, and it's the first time the NAT sees that. So there is no way your machine here knows what is the IP address and the port number that is allocated to that, except if this port number is statically configured in your NAT. So practically, one solution to this problem is to go into the NAT and do something. It's called punching a hole in the NAT, by analogy to the fact that a NAT is like a firewall that prevents communication to happening when you don't know the port number. And this is why some applications sometimes don't work if they require a server here at home. I mentioned a server for controlling your home, but there's another very popular application. There are families of very popular applications that use servers. Those are all the peer-to-peer applications. If you use Skype or WhatsApp for calling someone, one of you is the server, the one that is receiving the call, and the other one is the client, the one that's initiating the call. So you have that problem with all those applications. Those applications solve the problem by having a third party somewhere in the internet used as a directory service. So typically, if you use Skype to call someone, you will first send a message to a Skype directory service. And this guy, if Skype is running on this machine, it has already contacted this Skype service on the internet so that the firewall, the NAT here knows a certain mapping here. If the mapping, the transformation of IP address and port number is fairly brutal, independent of the correspondent host, in other words, if the NAT allocates a fictitious port number and the IP address that is given here the same, but independent of whom you're talking to. So if I look at the previous thing, here I allocate to this port number and this IP address this port number. By doing that, the simplest is to do the mapping as I have done. In this case, the mapping is independent of whom I am talking to. So if I do that once, that's good enough. Some NATs do that. Some other NATs are a bit more contorted. They do an association that is valid only for a certain destination. If that happens, Skype will not work well. You will not be able to directly go from this machine to that because the NAT will refuse to do the translation if the packet don't come from the host with whom Skype has talked here. If that's the case, Skype will not work peer-to-peer. It will need to go through an intermediate server that will relay all the traffic. If your NAT has this independent property, then the traffic will be able to go straightforwardly. But you need support from the application for that. This is, for a long time, NATs did not work well. The very first messaging application, like some of you are perhaps old enough to remember Microsoft Messenger, and so they were not as smart as Skype. In fact, the fortune of Skype came from the fact that it solved automatically this NAT problem. So those precursors of Skype did not solve the problem automatically, so you needed to be an expert in TCP/IP and be able to go to your NAT to program an association and give that information to whoever would call you, which admittedly is not very convenient. So this is how a NAT works. One question: when a NAT has a packet to forward, and by some reason the association already exists in its table, what kind of lookup does the NAT do in its table? And the majority says B, and the majority is right, as most of the time. It's an exact match, because you need to find exactly the combination of port number and IP address. So that's a very different way of performing the match than in an IP router. That will tell us that the NAT solution is not very scalable. It works well for a relatively small set of machines that are in the private network. If you had 1 million machines in this private network, then for every packet that receives, you will need to find in a table of 1 million and more, because there might be multiple port numbers. You will need to find exactly which correspondent host which line you need to activate. You cannot do aggregation like you do in the internet in a router, when we use longest prefix match. Question? If you had 1 million machines here, probably you would not have a single IP address. So you could use a block of IP addresses.
Okay. But if you have only one IP address, it's not feasible to...
Probably not, right? The port number is 16 bits. So it's 16 bits gives 64,000, so it's not sufficient for a million, correct? But you can do it. It's called carrier grade NATs. If you have here a company and not a home, you may have, for example, a block of addresses which is only 24-bit prefix. That means you have 256 address, and then you can have a large number of hosts here, and you do the same thing, except now the only thing that is constant is the first 24 bits of the IP address. But being an exact match, it is not a solution that will scale very well to extremely large number of machines. In the reverse direction, what may happen? So I'm showing in red here the direct communication from LAN to WAN, and the question is in the reverse direction, from WAN, which is on the right, to the LAN on the left. I close in 5 seconds. And the correct answer is, of course, the destination port. In fact, it's not just the destination port, but also the destination address from the WAN, which means from the internet, to the local area, which is illustrated here, right? Voila, that's the story of NATs. NATs are primarily deployed for IPv4. For IPv6, for a long time, people have been saying NATs are required because with IPv4, we don't have enough addresses. Therefore, for IPv6, there's no need for a NAT. And that's why there are very few IPv6 NAT implementation that are available. However, the need might arise to have private IP addresses for other reasons than just be able to reuse one IP address. Which other reason could you imagine? I mean, imagine you're running a company, you have IPv6, you have as many addresses as you want, but still you would like to have some private addresses. For security, yeah, exactly. So that could be a reason for one element of security, which is providing some form of isolation. By having private addresses, you minimize the risk that people connect to those machines. In order to connect to a machine that has a private address, you need to have a NAT or an application gateway or some other machine on the way, which might be easier to fortify than if you simply are connected with public addresses that may leak through multiple ways. In the labs, we use in INF 019 some form of IPv6 addresses that are separated from the rest of EPFL using a very specific trick. It's almost equivalent to having NATs, but it's called 6-to-4 addresses. We'll come back to that a bit later. There are addresses that are also not part of the normal IPv6 addresses of EPFL. Now we'll continue with a few more details on some of the things we've already used a bit in Lab 0 in particular, which is subnets and masks. We know already the main story, so I repeat it because it's essential to the understanding of IP. All systems need to know the mapping between the local area network and the addresses. And this is done by having to know what is their prefix. And the prefix is coded with a subnet mask. A corollary of that, or another way of that, which is, again, repeating one of the principles of IP, is if this machine, ED2IN, which is this machine here, this is a snapshot of a part of EPFL. So assume this machine has a packet to send to 128.178.15.7, which is this machine here. It's a DNS server. If this has to send to that, it is in the same local area network as this on one of its interfaces. This box is a router. It has 3 interfaces. It is on 3 different local area networks. And the principle of IP is if you are in the same local area network as a destination, you send directly to it. Sending directly means you use the local area network communication mechanisms to send the packet here without going through an intermediate router here. So in that case, it will be sent directly, which means putting the MAC address of STI-SUN1. If in contrast it has a packet to 156.24 LRC-SUN-S, which is not in the same LAN, it will need to go to the routing table and find what is the next hop. And in order to know this, it needs to know what are the prefixes that are on link with itself. On link means in the same local area network. Or another way to say this is that have the same subnet, and you know that by looking at the mask of your interface. Here, this is a snapshot of the routing table of this router here. Hosts also have routing table. You can see things like those 3 prefixes are on link, that means they're directly reachable. And you find the interface, that means ETH0 corresponds to this subnet. It's one way of saying the same. Here, this entry means anything that goes to the subnet 156, so this one, has to go to this next hop, 182.5, which is this machine. So this, we are here at this machine. It knows that this green subnet is reachable via this IP address here. And everything else has to go to the interface 10.1, which is something here on the backbone of EPFL. Here. So that is an example that I'm repeating of IP forwarding. And of course, the use of subnetwork and mask is that to implement this principle that one IP subnet must correspond to one network part. I think I mentioned 24 bits for EPFL. It's not true of all. If you go to the wireless network of EPFL, you've probably discovered that the network part is smaller. But those are typical values you find around 24 for IPv4 hosts. For IPv6 network part, very often you find 64 bits, which are indicated here. Right? We have seen how we identify the prefix is by applying a mask. Why a mask? Why is it called a mask? Why don't we say simply /24 instead of saying 255.255.255.0? Well, the idea of a mask is making the implicit assumption that you do a bitwise AND of the mask and the address to find a result. So here, if you do the bitwise AND of this address and that, you will find something equal to the prefix and zeros at every place where you are not in the prefix. And to check whether a destination address is on the same local area network as you apply the mask to the destination address and to your address. If the result after applying the mask are equal, that means you are both on the same destination address. This was how this was implemented in the first implementation of an IP routers in 1979, and this is why it's called a mask. But today, we can say 64, for example, instead of a very long list of F. Typically for IPv6, we will say subnet prefix length. Incidentally, the concept of a mask means that the prefix could be anywhere. In theory, you could have a prefix which is made of the first 8 bits and the bits from 17 to 24. I'm not sure it's very meaningful to do it, but you can try it on some systems and see if it works. If you do a bitwise AND, the bits don't need to be contiguous. That was an implicit assumption of the system, which is not true, at least certainly not true in most systems today. There is a folklore around the IPv4 addresses, which is called the IPv4 address classes. That tends to disappear, but unfortunately you still find some literature and technical guides that speak of a class A, class B, class C address. This is obsolete. This is a classification that does not mean anything today. It meant something many, many years ago, 25 years ago. The IPv4 addresses were grouped by classes, A, B, C. D and E still exist. D is multicast, and E is reserved. But A, B, C were meant to represent different sizes of network. So in the imagination of the inventors of TCP-IP in the 70s, there would be 3 types of networks: the big, the middle, and the small. The big one would be companies like IBM, MIT. The middle ones would be campuses like EPFL, and the small ones would be you and I at home. They never imagined, of course, that we would have so many devices with so many addresses. And the class A is the networks from 0 to 127. 127 we know is a private, 0 with a private, but is a loopback address, but those ones are formally class A. Class B is 128 to 191. You recognize EPFL address. That has the very beginning of class B, so EPFL was one of the very first institutions to have an IP address. Class C starts at 192. And the idea was that a class A network, the prefix is 8-bit. A class B network, the prefix is 16 bits. And the class C network, the prefix is 24 bits. So that would mean we don't need a mask if we have that. If you have a large company, you would have a class A network. And then you may have a huge bridged network with everything organized your own way. Remember, at the beginning, the internet was not necessarily created with the idea that IP is the protocol to interconnect everything at the last level. we assumed that there were local area networks between the systems. And the original internet was really the interconnection of local area networks. Some of them were large. Of course, very quickly it was observed that this does not fly, so this is not now obsolete. There's no reason that the network mask is related to the values of the addresses here. A little quiz here. I'm showing a diagram with a number of hosts and intermediate systems, and I'm asking what could be the address of host A. Is it the one that is proposed? Does it work or not? Nombre de choix. 3. I close in 5 seconds. The correct answer is B, the majority. Why is that? Well, we have a bridge here. That means that those lines mean that host A and this here are in the same local area network. A bridge is an Ethernet concentrator. It is a box to which you connect, and you are in the same local area network. We'll come back to what bridges really are next week. But right now, what it means for us is that if two systems are connected via a bridge, they are in the same local area network. Now there is this address here. The masks are 24 bits, so those two addresses are incompatible. Doesn't necessarily mean that A is wrong, but at least it's not possible to have this configuration here because of the prefixes that are different. The TCP-IP architecture says if you're in the same subnet, you should be in the same LAN. You're in the same subnet if by applying the mask we find the same prefixes. So those two machines, those two interfaces, this and that, are in the same subnet. Therefore, they should be in the same LAN. Of course, if you do this, you're violating the architecture. Perhaps it will work. If you find a trick, we've seen that with NATs, it's possible to violate. But if you do that, you're not doing a normal configuration. Yes, question? Okay. Of course, if you do this, you will not go to jail and your machine will not explode. But it will not be able to communicate. For example, if the true subnet prefix is this one, and if this is a router, when somebody has a packet coming from the outside going to this destination, what will this machine do, for example? Or if the packet comes, where is the outside here? If the outside is here, and if it comes to this machine, then the packet will be forwarded by whatever intermediate system here to X, if X is a router. And now the router will analyze the destination address. It will say 77.2 is on this interface. It will put it on this interface in this network. So packets to this destination coming from the outside will follow this path. They will come here. Right. They will never come here because this machine, when it has a packet to that destination address, it does the analysis of the subnet, and it knows I have to send it to a router. So I have to look at my routing table where to send it. You will not even try to find whether it's possible to reach A. So if you do only this, it will not work. Host A will not be able to connect to the rest of the world. Yes?
Because an entry without completely defined by the address of host A. Does that say that the host A is only?
If you add an entry, where in this box? Yes, so assume this is a router, for example. Then if you want this to happen, you would need to do something special here. You would need to instruct this router that this address is on link with you, is not, in fact, going here. So you would need to put what is called a host route. You can put in the routing table some instructions saying this specific prefix, which is a 32-bit prefix, is on this interface. And then the rest is there. So that would work. You can do that. Yeah. Which means you are manually configuring in the router the fact that this machine has done this violation. At ETH, the ETHZ, so in Zurich, the subnet mask, I said, for the wired network is 26 bits. Or the subnet length is 26 bits. So if you go there, you connect in an office, and you have to manually configure the subnet mask. Or if you use automatic connection procedure and you look at your subnet mask, what should you see? I close in 5 seconds. The correct answer is D. Well, it's a binary digit computation. How am I explaining it here? 56. Here is the explanation. So if we take the pain of writing all this in zeros and ones, this gives this. 3 groups of 8, 24, plus 2, 26. And now you need to convert that to decimal. This is 255. This you must know. And this is a bit more tricky. You can use a calculator. Or you can know that 1 corresponds to the power number 7 of 2, so 128. This is 64. 128 plus 64 gives 192. If you don't know that, you use the calculator. So this is the subnet mask you should see at ETH. We find here that the use of decimal representation for binary digit is very clumsy. It's far from obvious. Well, if you're very used to it, of course, it will look familiar. But it is not at all obvious that that means, in fact, 2 bits, the first 2 bits equal to 1, and all others equal to 0. Right. The subnet broadcast address, broadcast means we send to everyone. And we have seen that the broadcast address is all ones. So you should not give to a host an address which is corresponding in binary to all ones. That means broadcast to all. What is the subnet broadcast address at ETH? I wait until the majority is right. I stop in 5 seconds. And the correct answer is C. It's tempting to say E because of the 255, but the correct answer is you should put 111 everywhere here. And since the address, the prefix started with a 0, then you have to add the first 2 bits that are 0, the last 8 bits are 1, the last 6 bits are 1, that gives the number 63. Now why 63? Well, it's 64 minus 1. Therefore, this is the broadcast address here. Voilà, that's all we will see for this part 1. We've seen NATs. NATs, I mentioned the use of NATs at home in corporate networks. Of course, you perhaps have already perceived another use of it. It is when you are in a virtual machine. In the virtual machine environment, we also give private addresses, so we're in the same scenario as at home. And if you want to communicate to the real world from the virtual network that we have in the virtual machine environment, we also use a NAT. Voilà, we do a break and we resume at 1:15.